Hi Gr9s. If you got stuck with any of the mixed calculations on page 14 to page 14 and 16, then you're watching the right video. So let's go through some of those answers. Convert the following masses to weights. If any of them are not as SI units for mass, remember the SI unit for mass is the kilogram, then you need to first convert them. So 5 kilograms, you don't need to do any conversion. 5 kilograms you can keep as is. The formula: weight Fg is equal to mass times gravity, which is equal to 5 times 9.8. You can put it in brackets rather. 5 times 9.8, and 5 times 9.8 will give us 49 newtons. So the weight for A is 49 newtons. For B, we first have to convert. So 300 grams is the same as divide by 1000, or 300 grams is exactly the same as 0.3 kilograms. So if weight is equal to mass times gravity, mass is 0.3 kilograms, gravity on Earth 9.8. 0.3 times 9.8 gives us 2.94 newtons. And the last one, 2 tons. In the last video I would have told you about that. So tons is 1 ton is 1,000 kilograms, so 2 tons is 2,000 kilograms. You have to write your formula out every time. So mass 2,000, gravity on Earth 9.8, 2,000 times 9.8 will give us 19,600 newtons. So we've calculated those 3 weights. Alright, Yoda's on Luke's back while he's training him in the swamps on Dagobah. Yoda has a mass of 44 kilograms and is being carried at a height of 1.7 meters relative to the ground. What is Yoda's weight? So let's assume that we can actually write a little note here, that the gravity on Dagobah is 9.8 meters per second squared. Alright, so weight Fg equals mg, mass is 44, gravity is 9.8, which gives us a weight of 431.2 newtons. What's Yoda's potential energy at that height? So the height that we had was 1.7 meters. So from the ground up to that height relative to the ground is 1.7 meters. Mass 44 kilograms, and they want to know the potential energy, EP. That's measured in joules. So potential energy is equal to mass times gravity times height. Mass is 44, gravity is 9.8, and height is 1.7. And that gives us 733.04 joules. Right, now this next question you may have struggled with a little bit, so I'll discuss it first. Definition of work. For work to be done, think of the work formula. Work is equal to force times distance. So if you exert 0 force, if I substitute 0 as the force into that equation, 0 times the distance will give you 0 work. Or other option is if you exert a force, so say for example you push against a wall and the wall does not move, so the distance that the wall moves is 0. Let's say you exerted 1,000 newtons against the wall and the wall moved a distance of 0 meters. 1,000 times 0 will still give you 0 joules of work done. So work is only done if the object moves in the direction that the force was exerted on. So if you push a car and the car's handbrake is on and the car does not move, no matter how hard you push, you've done no work on the car. If you push on the car and the handbrake is released and the car moves a distance of 1 meter, then we can say, for example, if the car moved 1 meter and you exerted 1,000 newtons on the car, that 1,000 joules of work were done by you on the car. Right, so now with this definition, Yoda is on Luke's back. So Luke lifted Yoda up off the ground, and so Luke did work on Yoda when he lifted him up off the ground, but no work was done by carrying him because he was only exerting an upward force to get Yoda up off the ground. So we can say Luke does work lifting Yoda as force and movement are in the same direction. Luke does work lifting Yoda, and the reason for that is because the force and the movement are in the same direction, and for that it was up. When Luke carries Yoda, they're walking horizontally, but Luke only exerted an upward force on Yoda to get him up onto his back. When they're moving horizontally, no work is done. Yoda with a capital Y. So when they were walking, no work was done, and the reason for that is because the force was perpendicular to the movement. Perpendicular meaning at right angles. So the force was acting upwards, but their movement was, if they were walking from right to left, their movement was to the left, and that angle between them is 90 degrees. Right, the most recent upgrade of the Batmobile has a mass of 3,175 kilograms, and it can travel at a speed of 370 kilometers an hour. So you should notice that that's not the SI unit for speed or velocity. Right, with boosters activated and is equipped with machine guns attached to the front, convert the speed to meters per second. If you don't know how to do that, you need to go and consult your scientific, your SI unit notes from last term, because we taught that work there. So 370 kilometers per hour is the same as 107. So is the same as 102,78 meters per second, and to do that you would need to divide by 3.6. So now that you've converted kilometers per hour to meters per second, we can calculate the kinetic energy of the Batmobile when traveling at its top speed. So the mass of the Batmobile is 3,175 kilograms. The velocity that it travels at is 102.78. And we need to calculate the kinetic energy. Remember, kinetic energy is measured in joules. Formula EK equals half mass times velocity squared. Just write that a little bit more neatly. Remember, this is actually on the denominator, so if you wanted, you could write it as this. It's all actually on the denominator. Alright, so half mv squared. So half times the mass is 3,175, and the velocity 102.78 meters per second. Remember, you need to square that. Please don't forget to square your answer. To square your 102.78, you must square your velocity, and only your velocity, not your mass as well. And that should give you an answer, if your calculator is in scientific notation mode, 1.68 times 10 to the 7 joules. Okay, if the machine gun exerted a force of 500 newtons on a bullet which has a mass of 50 grams, calculate the acceleration that the bullet experiences. So we've got a force of 500 newtons. We've got a mass of 50 grams. That's not an SI unit, so we need to say that that's actually 0.05 grams if you divide by 1,000. So we use our equation F is equal to ma, or F if you were dealing with weight, it would be gravity, and that acceleration would be acceleration due to gravity. But we're not dealing with gravity, so it's just F equals ma from Newton's laws. So our force is 500, mass is 0.05, and acceleration is what we're trying to solve, so you need to divide both sides. I'm going to do it in red. You don't actually need to show the step. Divide by 0.05, divide by 0.05, so that those cancel. You don't need to show what I've done in red. It's just for explanation purposes. Only the blue writing is what you show. So you do have to show 500 divided by 0.05 equals to acceleration. And so your acceleration should come up to be 10,000 meters per second squared. Remember the units for acceleration, meters per second squared. If the barrel length is 500, and that is really, really fast, by the way, which it would be, a bullet would have to accelerate from rest in a gun very, very quickly. So 10,000 is obviously a very big value. Whereas if you dropped a bullet, if you were just standing on the ground and holding a bullet and you drop it, it'll accelerate towards the ground under gravity, and gravity is only 9.8. And obviously 9.8 is much less than 10,000. Okay, so if the bullet length is 560 millimeters, not an SI unit, and the force acts continuously while the bullet is in the barrel, calculate the work that's done on the bullet during this time. So let's calculate the work done. Okay, so work is equal to force times distance. The distance is 560 millimeters. And if you convert millimeters to meters, it's 560 times 10 to the minus 3, or 0.56 meters. And the force is 500 newtons. Could give you an example and say that it's 500 kilonewtons for argument's sake. Okay, so you need to take your answer from the previous question and use it over here. Okay, so that's where the 500 comes from. The distance, 560 times 10 to the minus 3 meters. And 500 times 0.56 meters will give us an answer of 280 joules. Once the bullet has left the barrel, why is work no longer done on it by the machine gun? In order for work to be done, you have to be exerting a force. And once the bullet leaves the gun, there's nothing still pushing the bullet. The bullet is actually going to slow down due to air resistance. So because there's nothing still pushing on the bullet, there's no force on the bullet. And if there's no force, then there's no work. So if there's no force acting on it, then you know that work is equal to force times distance. And if force is 0, 0 times any distance will give you 0 joules. Therefore 0 joules of work. Right, why does the bullet eventually fall to the ground if it doesn't hit anything during its flight? So if you were to draw a little free body diagram for that bullet, I'll do that on the side here. So you've got the bullet and your bullet is actually moving horizontally because it was shot. Eventually it will slowly go down towards the ground. So let's say that the bullet's moving from left to right. So the gun was fired and the bullet started here and it's moving from left to right. So there's a bullet moving from left to right. It's actually got the force of gravity acting on it. Okay, and the earth is pulling the bullet downwards. So it doesn't just keep on going horizontally forever. Otherwise, it would eventually go round and round the Earth, and that's actually what rockets in orbit, satellites in orbit do. But because it's got the Earth pulling it vertically downwards, it's going to follow what we call a parabola path. So it'll eventually go down to the ground. I'll show you that once more. So it doesn't keep going horizontally, it slowly starts going down to the ground. So here's the free body diagram for the bullet. Arrow pointing vertically downwards, and that is the weight, the force of the Earth on the bullet. And you've also got a little bit of air resistance pulling it. If it was going from left to right, if the bullet was traveling from left to right, air resistance would be acting in the opposite direction, slowing it down. And we can call that FA. Okay, but the net force on the bullet, you can see by the length of this arrow, is much, much longer, so the net force is acting downwards. So the only force acting on the bullet is gravity, which acts downward. Therefore the bullet is pulled down to the ground. So the only force acting on the bullet is gravitational force, the force of the Earth on the bullet, and that acts downwards. And therefore the bullet is pulled or attracted towards the ground. Okay, number 4 and 5 are for you to do. Again, ask your teacher if you get stuck, and once you've done that, you can continue with the test prep. Notice that the test prep is out of, there are mark allocations for the test prep. There are actually past paper questions. So since it's out of 61 marks, you should be able to do it in 61 minutes. Please aim for that. And again, ask your teachers if you get stuck. Try not to use your notes while you do it, unless you really, really need to if you get stuck. But it's good practice to give you an idea of what the tests will be, so that when you write your July exam, you're more prepared for it. Thanks, grade 9s. Bye.